the common way of thinking about time is wrong. The wrong picture is that things happen and there's a big clock outside that ticks time. We have the false illusion that there's a common time, but there's no common time in the universe. All fundamental equations of physics have no direction of time. How does the universe evolve if we don't have time? It's not that there's no change in the universe. The universe is change. What we're describing in physics is processes. Evolution is the dancing together of all the variables, all the clocks, not the evolution in a single clock. It upsets our intuitive idea of just a single common continuous evolving time. We can formulate quantum mechanics in an exhaustive way without ever saying this variable is a time variable. So what exactly do we mean when we talk about time? When we think about time, we think about the sequence day, night, day, night, day, night, year after year, the counting of events. Newton, to build his theory, made a bold assumption that there is something else beyond this counting of events, an entity that flows by itself independently. Of course, being Newton, he called his own notion the true time and everybody else's notion the vulgar time. But that's because he was a bit of a jerk. What Einstein realized is that this self-existing time that Newton was referring to, it's actually real. It's part of the gravitational field which we call space-time. The non-intuitive aspect of that is that the passage of time depends on where you are. And that was a major step ahead in understanding nature. In general relativity, there is a variable little t, which people call time, but it's not clock time. It's just a label for, bookkeeping. You might have a T1, a T2, a Tn. You can have very different clocks. There's no single common variable which is called time. What the clock actually is measuring is how much gravitational field there is between one event and another event. So it's a physical measurement of a quantity. Understanding which one is the right time variable, that was a wrong question. So the Schrödinger equation, when you go into quantum theory, you have somehow to adapt quantum theory to this way of thinking. So you have to generalize quantum mechanics to be coherent with the fact that this clock time and this clock time may be different when they move. The best way to formulating it is not to use at all this extra t variable, which is used in general relativity, but just talk about the clocks. Talk about what we actually measure. And in fact, when you write the quantum gravity equation, that variable disappears. And people were panicking, oh my God, we lose time. But we don't lose time. We have many possible times. To the extent in which we understand the world in terms of fundamental equation of physics, there's only one that has a direction of time, which is the second law of thermodynamics, and that's a statistical equation. Everything connected with the time orientation is a statistical phenomenon, because the world is in a state in which entropy is de facto growing. We see a glass that breaks in pieces, we never see the opposite. This is a property of the world. The difference between a hot cup of water and a cold cup of water, just the molecules of the hot cup of water move much faster. So temperature is essentially the average speed of the velocity of the molecules. And it's in this averaging that we get the thermodynamical quantities. We get these notions like heat. And that's key point. All the phenomena which are oriented in time involve things like heat and temperature. The thermal time hypothesis, I introduced it with a great mathematician, Alan Kohn. The key point is the statistical state of the universe picks up a variable in the direction of which entropy goes, and that's what we call time. We are so used to time-oriented phenomena that it's hard for us to see the connection between the growth of entropy and time. For instance, we have memories of the past, but not memories of the future. We can decide where to go to dinner tomorrow, but not where we go to dinner yesterday. So where is the entropy here? We are phenomena which are time-oriented ourselves. We are like candles. We burn free energy, we produce heat. When you think, your head becomes warmer. So we are time-oriented. That's why we think, oh, it's a really natural, intuitive, fundamental thing. Not because it's a fundamental part of the world, because it's us. We connect to entropy very directly every time we perceive time as flowing in a direction. What we are perceiving, it's entropy growth. Part of my thinking about science has given me a perspective about the passage of time, about myself, which is much less dramatic than when I was younger. There's something comforting in realizing that the way we see the world is just a very small, partial take on the world. We have to live with the multiplicity. We have to live with complexity, like in life all the time.